Lecture 2. I think this one also in the column I put as lecture 1. Variables, calibration and sensor characteristic, random error and statistics. All these things actually happening at the sensor parts. Okay, sensor parts. Now we go to details. Now this, and I have to warn you that these parts have mathematics. Okay, okay. Previous parts only just a simple knowledge. Now we go now more to mathematics, especially on the statistics. Statistics. Okay. Sikit lah, maybe in 50 minutes. Sebab apa? Sebab we have friends just coming, so I think I just entertain him for 15 minutes. Tak apa, no worries. Saya tak ada masalah. This class will try to I hope that at the end of this class, I mean this bukan class at the end of this lecture notes, student can elaborate and discuss about the variables and parameters, and then you can design the calibration process. That's our aim. You design your calibration process, and then you elaborate several important sensor characteristics, and you can calculate your random errors. Okay, so I just want to get into only one thing here, which is the variables and parameters, and then we end the class. So the variables, like I mentioned in the previous class, is actually varies parameters that have various values. Okay, there can be various. Gravity, is it variables or not? Gravity, G. No, it's not variables, isn't it? Because it's fixed for the Earth only. But in the moon, different G. So can be variables. It can be variables in the universe, but on Earth it is a fixed value. It's not variables. And then we have displacement, velocity, acceleration. All of this is variables, varies, especially in automotive. When you study engine itself, there is a lot of variables. There's a lot of variables. The only thing is what kind of variables that we want to measure. Okay. Of course, three things lah: temperature, pressure, displacement. Only involve three things lah sebenarnya: temperature, pressure, displacement. Okay. Now you understand the variables. Now we go to the details of the variables. We have three things: independent variables, dependent, and extraneous variables. Independent is not dependent in anything. Example of independent. Any variables can be independent variables. Okay. In a system, the only thing is in the system, we must recognize which one is independent and which one is dependent. Dependent variables, of course, it depend on the independent. Any changes to the independent will give the different values to the dependent. And what is extraneous variables? Is the other variables around the system. It might be changed, it might not. So listen, I can show you this one in terms of this one, figures. So if we have a closed system like this one, so the independent is the displacement. It's independent of anything. It's only we give the input through the displacement. Either we push it or not. The pushing part is not variables. Pushing part is just the action from us. But the only thing is, every time the x or displacement, the piston moves, it will give the effect to another variables, which is the pressure, volume, and temperature. So PVT is the dependent. It always dependent to the x value. Okay. So and then this one very important, the extraneous. There is a lot of things that actually being extraneous variables. We don't know. The more you recognize the extraneous, the more efficient your system is, because the extraneous can be the can also be the noise to the system. Okay, that's our challenge lah. Independent and dependent, you can set which one is independent and which one is dependent. You can find a way, straight away you can find. Even you can set this which one is the independent and which one is dependent. But the extraneous variables is external. You don't know what happened. It might give the effect to the system, or it might not. But if the more you understand the extraneous, the better the system is, because it will give effect. Saya dah mark kat situ ujung sana. Noise, it can give interference to the system. Noise and interference. Okay. Last one, the parameters. Like I said, G, gravity, can be in our situation here, it's not a variables, it's actually a parameters. Okay, it's a parameters. What else parameters? The definition is it's a functional group of variables. It's actually a functional group of variables. It will give indications of the system. It will give indication of the system. For example, Reynolds number. Reynolds number is some sort of like an indication. If Reynolds number high, so it will give some indication of the system, what happened in the system. What else? Flow rates, also parameters. But is it varies? Yes, it varies. It varies. The only thing is, inside the parameters, it have a lot of variables inside. For example, in a Reynolds number, we have density as a variable, V, volume, velocity of the fluid, D, diameter of the pipe, dynamic viscosity of the fluid, which have a group of variables combined together and then to form the parameter Reynolds number. So you have to differentiate between what is parameter and what is variables. What do you want to measure actually? In your system, you use sensors. What things you want to measure? Parameter or variables? Variables. Yeah. We want to measure variables to make sure that we can build the parameters. Okay. We look on the variables, the type of variables. We have 3 of them, which is the first is independent, and then the other one is dependent, and the last one is extraneous variables. There is a notes over there. You can see. You can refer to the notes. I'm not expecting that you memorize the sentence because we are not in the school student. The most important is you can elaborate what is actually independent and dependent and extraneous. From name itself, we know that the independent variables is variables that independent to other variables. So the name itself can tell us what it's all about. The only thing that the tricky one is the last one, the extraneous variables, which is why it's called extraneous variable. It's extra variable. Sometimes we can recognize it, sometimes we cannot. Sometimes it just happened during the measurement. The more we learn about the extraneous variables, the more that we can eliminate the possibility of errors and uncertainty to the measurement. Because when we design cars, we put a lot of sensors in the cars. We don't know which part of the cars can give the wrong signals to the reading. Jadi that's why very important for us to put our brainstorm which variables can cause the extraneous to be the extraneous variables during the measurement. All right. I have mentioned about this one last class also, which is the example. This is a quite famous example. We have PVT as a dependent, pressure, volume, and temperature in the chamber as a dependent, and we have the motion of the piston as the X or the input variables, as the independent variables, and then the rest might be or might be not to be extraneous variables. The size, the chamber for pressure transducer, okay, the shape of the pressure transducer, the power source, the voltmeter, the reading from the voltmeter, and then all the things can be extraneous variables. It not directly, the most important is it not directly contact, not directly involved in these two variables, independent and dependent. They're not directly involved, but it may cause the changes to the reading by in this part, dependent. I think this wrong spelling. Betul lah? Betul lah? Alright, so I've mentioned also the last class about parameters. What is parameters? I think I've shown you a clear example here. I believe this is a clear example for me, for you to understand the difference between parameters and variables. Variables is the value that we put on the parameters on the sorry. Variables is the physical number, physical value that we put the value of variables. All these values, if we derive, you will get the parameters. So, for example, I include in the notes the Reynolds number and also the flow rates, volume flow rates. There is another example you can refer later on. Okay. The most important is we're not measuring the parameters. Okay, we are measuring the variables. Okay. And then this is quite important parts during the measurement process, which is we need to acknowledge the existence of these things, which is the noise and interference. Noise, like I said, is usually referred to the effect of extraneous variables. It causes the data to scatter. Sometimes worse, sometimes we can control. But most important, most of the time, if we cannot recognize what is caused for the noise, usually it will cause the randomness of the data, make the actual value that we want to measure hidden inside the noise. That's what we're afraid. Yeah, we're afraid that the original signal that we want to measure is hidden inside the noise. So that's the noise. And then the second one is interference. Interference, actually, it will not disturb the signal, but it make the signal move towards somewhere, some directions. Because of, for example, the humming from the audio system. Originally it starts slowly, and then after that it becomes bigger and bigger and bigger. But this actually comes from the original sound. I will show you this one. So this one is the best, for me, is the best explanation on the difference between noise and interference, which is, you can see, if the signal, you get this part, signal plus the noise, the signal, original signal is just 2 plus sine 2 omega t. So it's actually a very clean signal, but it plus with the noise to make the effect to the original signal. Imagine that the signal is same like this, same like this one, original. But because of the noise, so the signal hidden inside the noise. But still we can see the shape. But we cannot identify the maximum value of the signal. Okay, because the maximum value of the signal may be hidden inside here. So it just something like this, but it's hidden inside. So that's very important. We need to eliminate the noise and the interference causing the signal to move up towards some directions. It gives the new trends to the signal. Okay, so that's interference. If we remove the interference, it will back to the normal. Okay, so this is actually the difference between. So if what happen if a signal plus the interference plus the noise? Okay. You can see that it will be something like this lah. Something like this, something like this. So this is actually a signal plus noise plus interference. Alright. Okay. So that sounds very clear. So please make sure that you know what is actually noise and what is interference, what is parameter and what is variables. So these four terminology that we introduced from the last week until now. And then now we want to once we know what is the independent variables, what is dependent variables, what is noise, what interference, now we need to look into the experimental plan, test plan, because there is two conditions. First, when you build a sensor, you must make sure that your sensor works according to the specifications. So how can you set the specification for your sensors? You must do some kind of testing. So how can you make your testing for your sensors? By planning for the experimental test plan. That's the first one. The second one is when you have the sensors, how can you use the sensors? You cannot simply use the sensors as it is. You must make sure that you use the sensors according to what is intended to do and what is according to the spec. That's why you have to plan carefully for the test plan. For example, so this is actually telling you the step. So first is how that we set the test plan. The first is we have a few things. First is we need to be recognize the variables. Make sure that you know all the variables. Okay. For example, kalau fuel consumption on the car. Okay. So what is the variables involved? The distance, the fuel volume, what else? You name it. This is just an example. So example is distance and fuel volume consumption. And then which one is dependent and independent? The distance will be the which one is independent? For me, both of these is independent. Kan? So the independent is the input. Usually the independent is the input. What is the input? Okay, maybe the way you drive. Okay, the way you giving pressure to the pedal. This is how you. So the input. So the output will be the volume consumption and the distance lah. And then what else? Okay, so the extraneous, the accuracy of the odometer. The odometer you use to track the distance. It also have the uncertainties, so that might be the giving the extraneous variables. And then we have the way of filling the tank. How we fill the tank? We fill it full, or we fill it halfway, or we fill it very little, or we fill it like I have seen a viral video. Somebody filling the fuel, just shaking the car. Shaking the car, pushing the car. I don't know why. Why? I believe because of they want to remove the excess air, okay, so that the tank can be filled more with the gas. I don't know whether it works or not, but I've seen that videos. They struggle to shake the car while filling the fuel. And then we have also variables like driving routes, weather, road condition. All these things can be the extraneous variable. Okay, and then so after we recognize all the variables, then we need to find the parameters. What's actually the variables? What actually the variables that we measured can contribute to what parameters? We establish our own parameters lah. Yeah. Like I said, parameters give us the situation or the condition of what we measured at the time. So we establish our own parameters. Okay. For example, Hafizi parameters. What is it? Maybe Hafizi parameters are high, so that the fuel consumption is bad. Hafizi values parameters is low, then we give some sort of imagination of how we can imagine the situation happening to the cars. So we establish the parameters, and then we select the measurement technique, how we can measure all these variables, and then the last one is how we can do data reduction. How this is actually a display lah, data reduction. How can we post processing the data, because we collect the data, a lot of data, and then we have, of course, that data. Do we have to store all the data, or we have to store important information of the data? Okay, so we choose which one. Okay, usually we in terms of storage, we choose on the best data. We already filter the noise, we already remove the interference and so on, and sometimes you do another post processing to make sure that only single data can be stored. So it depends on us lah. So parameter design, system tolerance, okay, measurement techniques. Ni measurement techniques, and then the last one is data reduction, data planning for the display lah, kita kata. Alright, so remember all that steps lah. Remember all these steps. We have 6 steps. Okay, in experimentation plan, right? So if I give you some case, and I want you to design your own test plan, you use that 6 steps to design your own test plan lah. Okay. So another terminology that you have to understand is the repetitions and replication. What is a repetition? It's repeat. How can you repeat the measurement? Measurement can repeat. When you do measurement, you can repeat it a few times. A single measurement, you can repeat it a few times. Okay, that is repetitions. So every time you repeat, hopefully that the readings can be maintained at certain accuracy lah. And then also the second one is the replication. Replication is there we can replicate the measurement system that you do. You do testing. For example, if you use the test for fuel consumption kan. Fuel consumption test. Can we replicate the test that have been done in Kelantan and replicate the test in Sarawak? Can we do the same test? You think? We don't know. Maybe at Sarawak maybe the road condition is different, so we need to have a different test plan. So in Kelantan, there's different road conditions, different ground. So we need to do a different test plan. So different place, different test plan. So that means that test cannot be replicated. So usually we when we set up in the postgraduate level, PhD, masters, when we set up experimental test plan, we must make sure that our test setup can be replicated around the globe. Okay, Same with you guys. When you do in the R&D, you do tests in German, you do tests in Malaysia. Is it the same condition? Can we replicate or cannot? So this is things that we need to make sure that when we design the test plan, we make sure that this thing can be done. We can repeat the measurement and we can replicate the measurement. Alright, so now calibrations. Calibrations, the same related to the test plan lah. When we want to do the calibration, we must set up the proper test plan for the calibration. Calibration means we establish the value, we compare the value into a known value lah, a known value. For example, the length. We built the ruler. When we build a ruler, how can we calibrate the correct value of the ruler? So 1 cm, we're referring to what 1 cm? 1 foot. What is the actual 1 foot? How we can calibrate that one? For example, in mass, 1 kilogram. What is the value? What is it we compared to actually? 1 kilogram. So actually we compared to the original size of 1 kilogram mass in a museum, I think in UK, I think. So we comparing to that one actually. So there's a lot of copies for that one. For foot, I don't know whose foot is that. Kan? Kaki siapa? Whose feet is that? That be the actual ni. So that's why when we talk about I think old people in the village, they are actually using feet because easy for them to measure something. You just use a step, moving, and then they can actually using his own body lah as a measurement. That's why the old style of measurement is very easy. Hectare. Actually, it's very easy to use because you use our own body. Alright. Okay, so for the calibration, we will see after this. We have a calibration curve. Okay, so we have to check all the instrument that we have. For example, if you buy ultrasonic measurement, for example, if in the car, I think if you have ADAS, you know ADAS system. Every car have ADAS system. Now modern car have ADAS system. They actually recognize the distance from your rear car or front car, whatever, into the object that close to you lah. So they have to measure the distance. But before that system is set up, it have to do calibration every time. Every time you press a button calibration, you will calibrate every time lah. If you not pressing the button, then just remain as in the previous measurement. But ADAS system must be calibrated all the time. Make sure that it actually measuring the correct distance between your car, your rear parts of the car, sensors, to the actual object in that behind your car lah. So that calibration value is actually depend on the measurement. Okay, if you fail to do calibration, your measurement is incorrect, not accurate. Alright, so we have two kind of calibrations. Sorry, because this is actually just all terminologies. I think after this we have some calculations. And for that one we use statistical. So, but before we move to that one, we need to know the static calibration and dynamic calibration. For static calibrations, it just only depend on the magnitude. Okay, magnitude only. So the input value, because in static calibration we have two values, the input and output. Of course, we want to calibrate between input and output lah. Make sure that all the values is related. But the input value is controlled by the independent variables, and the output value is the dependent variables. Usually we want to calibrate the output with the input. The input is the known value. Usually the input is the known value. We know the value for the input. We give the value, and we see the output value. So output value is the one that we want to. It's very important lah. But this thing only we refer to the magnitude of the output value. So I'm showing the curve. So this is actually a calibration curve. Okay. I move forward. What's the okay? So this is the curve. Okay. So look at the input value is the one as the known value, the input value, and this is the output value. Okay, this is actually the one we want to measure lah. So we will establish a relation between input and output. Either is in terms of exponential, or in terms of logarithmic, or linear. It depends on the data lah. For this one, I think it looks like quadratic a little bit. So the m value kecurunan apa kecurunan? Gradient, sorry. The gradient will be different throughout the curve. Okay, because of this is actually a quadratic curve. So we have a linear curve, linear value lah over here. Tapi all locations have a different gradient. So the gradient is we call the apa dia? Sorry, I forgot the term. Sorry. Static sensitivity. Static sensitivity. K. It always dy dx of the curve. Always dy dx of the curve. If the curve is logarithmic, you have to find dy dx for the curve. If it's linear, and easy lah linear. Linear y equal to mx plus c, then easily m become the static sensitivity. Okay. If it is quadratic, you have to do dy dx derivation. Okay. In the previous semester, I always give a plot for measurement, calibration. I give a plot, input and output, and then you have to plot your own value. You have to use your graph paper, and then calculate the static sensitivity. Or if you cannot use your, if it is linear, you just simply can use that given value to find the m lah, kan? Kalau linear, kalau dia is not linear, you have to plot. Or actually, if it's not linear, for example, if I said this plot, it is in quadratic equation, you have to calculate the quadratic equation, and then you have to find the dy dx. For example this one lah. You have a few plots. Okay, you have a few plots, and then I said that this is actually linear. If I said it's a linear, so you can easily using the plots to generate the linear equation. So from that linear equation, you calculate the gradient. Usually I give you a linear lah. Kalau I give you quadratic, I give you a plot lah. Okay, I give you a plot. Or I just simply give you the equations. If I give you equation, and it's easy, you just find the dy dx for the equation. You have to differentiate lah the equation. Alright. So the statement there, dy dx, x equal to x1 means every x lah. Every x we have a different gradient. If linear, only one x. One gradient lah. Kalau linear. So this is actually static calibration. So if you go to the other one is dynamic calibration. Actually it's for the dynamic analysis. is involved two measurement, which it involves another measurement, which is the frequency content. The frequency content. So usually I didn't mention in detail for this one, but for this course we have to discuss in details mathematically how the dynamic calibration being done. We're going to use accelerometer. We're going to use usually accelerometer lah, to do calibrations. Okay, but we have the static calibrations and dynamic calibrations. We're going to look in details in the laboratory session later on. Alright, so I'm going to go to the last parts of the lecture today, which is the error. Okay, we have 5 errors, important errors that you have to know, which is the most important refer to the error is the measured value minus the true value. Okay, true value sometimes is just average from the whole value, that we measured, it become the average. Sometimes we use the average value as the true value. Okay, sometimes we already know the true value, and then we just minus the measured value to the true value. So that we call absolute error. Absolute error because because we minus the actual value that we measured and minus the true value. The relative accuracy is the percentage, which is the this is what we call absolute. E divided by reference value. What is reference value? Is the usually we use a range. Nanti kita akan I will show you what is the range actually. It's all about. But times 100, and then we can find the accuracy. Accuracy for the errors accuracy for the errors that we want to measure. Alright, so we move forward. So we have a lot of errors, which is a random error and systematic error. Random error, like I said, if you can recall, random error is related to the noise, because the noise try to randomize the data. So random error usually because of the noise, and systematic error is because of the interference. Because systematic error always, it actually remains the same value, but it actually bias or offsets from the original value. Okay, so this is systematic error. Systematic error is easy for us to recognize. It's easy for us to recognize and easy for us to remove. Find the source of the systematic error and you can have the accurate value. But random error is different. It's very difficult. Okay, the only thing we can eliminate the error is by properly do experimental test plan lah. Properly do experimental test plan. Make sure that we can recognize all these source of the errors. Okay. Alright, so in terms of figure, we can see that actually this is the same as what I mentioned previously. If you have interference and noise, so it's also happening. That thing, interference and noise, related to the repeatability and precision and accuracy. So if we have a noise, so it will have a random value, so it will scatter. So that one will give the will affect the precision. So it's not repeatable. It's not repeatable. Repeatability is very bad for the first one, the first line. Okay, that caused the random error. The second one is actually the true value, but it shifts towards upwards bias. Ada bias, ada offset. That offset, if we can eliminate, we can have a true value. Okay. But still, the precision is does not depend on the systematic error lah. The precision is will affect based on the randomness of data or the noise. Okay. So high precision infers a lower random error, better repeatability, and less variation between measurement. So to make sure that we have a high precision and high repeatability, make sure that we remove the random error. Alright. Okay, so this is just a simple explanation on the accuracy and precision. So this is actually a high repeatability but not accurate. This one is high accuracy, good accuracy, high accuracy, good repeatability, but that one bad in everything. Alright. Usually if this one happen, that means your system is good actually. You only have to remove the systematic error. Okay. Okay. Alright. So okay, this is the range. Okay, this is the reference that I'm talking about. If you look at the sorry, I have to move again to this one, the reference value. Okay, the error, the absolute error here, okay, over the reference value. So the reference value is referred to the range. So this is the range. Okay, this is the range. So we have two kind of range. Full scale operating range. Okay, look at the y and y max and y min. Y axis. We have a y axis, the y axis and x axis. Okay, so if I say find the error based on full scale operating range or FSO, you have to make sure that you find the range at the x, the y. If I say in terms of input range, FSI, so you use a range as the x. Look at here. If I can go back to the, if I go back to the calibration curve here. Okay, so what is actually the full scale output for this one? It's 0 to tak apa 10 some 9. So if I say full scale input, it's actually from the 0 to 4. Okay, so you have to recognize what is FSI and what is FSO. Okay. Alright, and then sorry, I move forward. So this is actually as an example of the range. Okay, another terminology is the resolution. Is actually the least significant digit that can be read by indicator. Okay, actually the scale. If you have the scale. If you have the scale, like this. So the smallest indication here is the resolutions of your system. Okay, so if you have a scale here, okay, this is actually the resolution of your system. Okay, the smallest scale in your measurement. Okay, so uncertainty, this one involve the calculations. Now we start to have a calculation. So I stop at the uncertainties. We continue on the Thursday class. From here until the statistic, until statistic. So you can expect that we can have some kind of quiz during the class on Thursday nanti, yeah. Alright, so with that I stop our class here and the uncertainties. So we will finish on Thursday, and then the next week we're gonna go to the new topics on the signal analysis. Alright, so thank you very much for your attention. So see you on Thursday class.